Okay, good morning, everyone, or good afternoon, everyone. It's just past noon now, and we're going to start with our grand rounds. My name is Kuram Khan. I'm head of service gastroenterology at St. Joe's, and our presenter today, I'll do a quick introduction. Just before we do, we'll also mention that the rounds are being recorded and will be shared and available on YouTube for reviewing afterwards, in case you missed something. Dr. Charlie Wang is our guest speaker today. He's actually a gastroenterologist, but the topic is GI. We're always at the cutting edge of things. So today we're talking about artificial intelligence and Hitchhiker's Guide to AI, a journey from basics to leading edge. Some of the objectives are to learn how AI and LLMs actually work and to explore Epic's leading edge AI features, including cloud computing, generative AI suite, Cosmos, and Curiosity. A quick bio about colleague Dr. Wang. He is I mentioned, gastroenterologist who's been in practice for over 15 years, initially in Bradford and now in Hamilton. He has an interest in data science and digital health. He has a certificate from Waterloo in data science and is also currently completing his master's degree in e-health at McMaster. And he's also, as part of that, been doing a stint as a chief medical information officer intern at St. Joseph's here. So today he's going to be sharing with us this presentation. I'll hand it over to Dr. Wang. Go ahead, Charlie. Thanks.
Thanks, Graham. So we'll get started. So we'll start with the land acknowledgement. So we acknowledge that St. Joseph's Healthcare Hamilton sits on the traditional territories of the Mississaugas and the Haudenosaunee nations, and is within the lands protected by the Dish with One Spoon Wampum Agreement. This is a treaty between the Anishinaabe, Mississaugas, and Haudenosaunee that bound them to share the territory and protect the land. Subsequent Indigenous nations and peoples, Europeans, and all newcomers have been invited into this treaty in the spirit of peace, friendship, and respect. So the title of the talk is The Hitchhiker's Guide to GI. So don't panic. We're going to talk about the basics of AI and how Epic is actually on the leading edge of incorporating AI. So the journey is understand the basics, and I think I get a bit technical, but try to simplify so people can understand. And then I'm not sure how many people are aware of all the different AI features that Epic has. So we'll go over quite a few of them. So these are my conflicts of interest, some ad boards and consulting fees, but nothing of relevant, no conflicts for this talk. So I was asked to kind of simplify the talk into one main idea. And the main idea is basically AI in society and in healthcare is here to stay. We should embrace it, understand it, take advantage of it, or we will risk being left behind. So this is an AI generated image of, going from being a sloth to being a cheetah. These are the CanMed roles. So basically all the different CanMed roles I think are covered. So the agenda, so the first is to talk about what artificial intelligence is, some of the buzzwords you hear a lot, deep learning, generative AI. So we'll go over what all those things are. And then we'll talk about kind of 4 of the major things Epic is doing in AI. And the last 2 are bolded because I think those 2 are the ones that, to me, are the most exciting and interesting. Okay, so here's my background. So why am I giving this talk? So I am not a statistician or a computer scientist. I have been in practice for a little over 15 years. Previously I do have a master's in ClinEpi, so I have a little bit of a statistics background. I've obtained a certificate in data science. I'm currently in the eHealth Master's program at McMaster. I did 8 months working with Dr. Perry as his Chief Medical Information Officer intern, and I'm hoping to be the soon-to-be incoming Associate Chief Medical Information Officer at St. Joe's. So those discussions are happening now. So why am I giving this talk? So I learned data science and AI essentially from scratch. I've been able to integrate it with some of my clinical, administrative, and research background, and hopefully I can pass along what I've learned to others in sort of a simple, easy to understand manner. So we'll start out with a video. This is taken from YouTube.
Fact, this entire speech and video are not real and were created using deep learning and artificial intelligence. And in this class, you'll learn how.
Okay, so hopefully after the end of this talk, you'll sort of know how this was created. Okay, so we'll start off with what is artificial intelligence. So fake Obama mentioned deep learning, artificial intelligence. So what are those terms? So this is the nice picture. So kind of the umbrella term is something called artificial intelligence. And so that is trying to train computers to think and behave like humans. Then under artificial intelligence, you have this subgroup called machine learning. And that's basically when you try to get the machine to learn. And then a type of machine learning is something called deep learning, which is where you use neural networks to do that machine learning. And the data science is sort of a little bit, has a bit of all of those things incorporated into it. So we'll start off with a quick example. So this is something I did for one of my classes. So the question is, if you use today's data, can you predict tomorrow's emergency department ambulance offload time? And so if you think back to your undergrad or medical school days, this is what's called a regression model. So you have a bunch of input variables and you try to predict an outcome, a y, like a y equals equation. So these are some of the predictors that were put into the model. So, does the day of the week impact tomorrow's ambulance offload time? Does the month, does the phase of the moon? We sort of think, well, full moons are busier days, and so does that impact emerge volumes, ambulance offload times? So you can kind of input a bunch of predictors, and you see how well these predictors are able to predict some outcome. And traditionally, if you think back to statistics, you had kind of the two basic models. You have something called linear regression and logistic regression. So this might take some of you back. So this is, when you plug in into a computer to do a linear regression, you get all your individual X variables. You get a p-value that tells you how important each particular variable is in predicting the outcome. So in this example, it's tomorrow's ambulance offload time. So, it's a very manual, subjective process. So you can look here, well, if the World Series are on, it has a very high p-value. So probably being in a World Series time does not impact ambulance offload time. So then you would maybe, get rid of this variable the next time you run your model. Same with, total admit no beds and emerge. High p-value, so may not be important. So you go through, you iterate, you take out the ones that have the highest p-values, you rerun your model over and over again, and then you're left with a set of what you think are the most important variables. But again, this is subjective. It's not time efficient. And so can machines do better? And the answer is, people have tried, and there's lots of what are called machine learning models, which basically take that manual process that we do in our minds, and the machine does it. So you basically tell the machine, I want you to minimize this particular type of error. And it iterates, it goes through what it does, and it finds the most important predictors that minimize whatever the error is that you tell it to minimize. So there's different types of algorithms for machine learning, support vector machines, decision trees, random forest, k-nearest neighbors. I see more and more papers using these type of models. So it's important to kind of know what they are. They're a type of machine learning algorithm. And neural networks are really not anything that special. They're basically a type of machine learning algorithm. And just as a side note, super interesting. So you can actually combine different models to improve your output. So you can say, well, I want both a linear regression and a decision tree model, and see if combining different models will give you a better result. And humans can't do this. You can't do this with traditional statistics, but you can do it with machine learning. Okay, so let's focus in on neural networks. So again, it's not anything special. It's really just another type of machine learning model, but it is the most powerful machine learning model, especially when you have lots and lots of data. And in recent years, it's really grown and taken off because everything we do now, somebody's collecting data on everything. We have lots of GPUs, NVIDIA is making lots and lots of money because they're selling lots and lots of GPUs. We're building lots of data centers to collect the data and analyze the data. And then, there was a trend of open sourcing, so companies would share the different models that they came up with. That trend is reversing. I think, with OpenAI, people are now not as open to sharing because now, the competition to see who has the best model. But they have really taken off. And if you look at this chart here, so as data gets bigger across the x-axis, your traditional algorithms don't perform as well. So as you get more and more data, you have limits with your regular statistical models and traditional machine learning models, and your neural networks really start to really take off. Now, we'll spend a few minutes talking about, well, what is a neural network? Like, what is the neuron in a neural network? So this is kind of what it is. It's actually fairly simple. So you have a bunch of inputs. So if you remember back to algebra, y equals mx plus b. So your y is equal to some sort of x input. You have a weight, a bias, and you feed it into some sort of function. So we'll go over it one by one. So your input is basically you have a variable, you multiply by a weight, another variable, multiply by a weight, and you have a bias, and you add all these numbers and you get a number. So that's essentially what you get. You get a number that gets fed into this little circle, which is a function. And so what is the activation function? There's really only three that are used commonly. So a function is basically a curve. You put in one number and it gives you another number. So if that left side, you feed in a number and say that number is -1, then your function outputs another number. And if we take the sigmoid function, it's 0.25. So really all that neuron does is take one number and transforms it into another number. And then you have an output, your y. Now, what makes it powerful is that all of these weights and biases can be individually tuned to make your model very accurate. And so again, in this example, you have 2 weights and 1 bias. If you combine a bunch of these neurons into what's called a neural network, then that's where you get really powerful ability to have accurate results. So deep learning, fake Obama mentioned that word deep learning. So deep learning is really when you have a neural network that has more than 2 layers. So this is layer 1, layer 2. And each layer can actually have as many neurons as you want. You can have 1,000, 100,000, 1,000,000. And then you can have multiple layers. So you can have one layer that's 1,000,000 neurons, another layer that has another 1,000,000 neurons, and then you have as many layers as you want with as many neurons in each layer as you want. And then if you think about the number of weights that you can fine tune, that's how you get the power of the neural network. If you look at, flagship LLMs like ChatGPT, Gemini, they have, 1.5 to 2 or more trillion weights. So they have more than 2 trillion individual weights that you can adjust to make your output very, very accurate. And so that's how you get from traditional statistics and basic machine learning models where you have a bunch of numbers, you try to fit a straight line. What's the best straight line you can fit through a bunch of data points? To neural networks where you have, trillions of weights, you can basically fit, a line through each point to make a very, very accurate model. So that's the power of neural networks. So how do we go from that to natural language processing and large language models, LLMs? So language is a sequence. So it's not just a picture, it's a sequence of words. And so in order to process words, you have special types of neural networks that process sequence data. So in the past, you had things like what are called recurrent neural networks, long short-term memory networks, gated recurrent unit networks. And those are not very good. So for the longest time, people could not actually do much with language. Then in 2017, Google published a paper on a different type of neural network architecture that could process sequence data and words much more effectively. So this is a paper from 2017. It's called Attention is All You Need. And they introduced this concept of what's called a transformer. So again, that's a term that you may hear in the news. And if you look at the word ChatGPT, GPT, that T in ChatGPT stands for a transformer. And so all of the kind of modern LLMs are based on this transformer architecture. Okay, so we have that. So how do we get, though, from a neural network to be able to do something like ChatGPT? So for that, we need to know what generative AI is. So this is kind of another Venn diagram. So we talked about what AI is. We talked about machine learning. We talked about deep learning. And generative AI is a type of deep learning. And this is where your neural network can get trained on some data and generate new data that is similar but not quite the same to the training data. So it generates something new. And so again, so what it is, so it's a machine learning model, a neural network that takes raw training data, it learns the underlying pattern of that raw data, and by learning the underlying pattern, it can generate new data that is very similar to the old data, but not the same. And it does that by doing something called representative learning. So again, another type of learning. So you have machine learning, deep learning, and then this is called representative learning. So what representative learning does, it's actually pretty intuitive. So you have what's called an encoder and decoder network. So you have your encoder that takes some sort of input data, it learns that data, and it creates a simplified representation of that data. That's what's called representative learning. So it takes some underlying data, the encoder learns it, creates some sort of representation of what that underlying data is, feeds that to a decoder, and that decoder then can recreate that original data. So the encoder learns the most useful features, and the decoder then learns how to reconstruct that. And in this area here on the right, a very simple example. So if you have a sequence of numbers, 2, 4, 6, 8, 10, the encoder will look at that, and instead of trying to memorize the sequence of numbers, it says, well, this is just adding 2 to each number. So it can simplify that and represent that sequence of numbers as n plus 2. Then your decoder looks at n plus 2 and then can recreate that sequence of numbers. So that's actually very simplistically what it does. So then how do you apply this to, say, a picture? So you have an image of a person. Your encoder learns that face and assigns, what are called latent attributes. So it assigns code to represent that face. And then the decoder takes that code and recreates the face. But every number can be a bell curve. So then if you say a smile on this image here on the left is 0.99, what if you change that smile to be a 1.1? And then you take skin tone, the picture is 0.85. What if you made that 0.8? And then you do the same thing with gender, beard, etc. You just alter the number slightly, then what happens? You can actually create a whole new picture of a face. So people have done this. So there's this website, thispersondoesnotexist.com. So if you go there, it'll basically create a picture for you of somebody that does not exist. And it uses the same principle where it kind of makes little changes to that code, that representation of a face, makes tiny changes, and creates a whole new face. That's a pretty cool website if you guys have, anybody has time to go look at it in the future. Thispersondoesnotexist.com. Then what else have people done? Well, I think everybody has heard of deep fakes. So it's actually based on representative learning. So I'll go through an example. So say you take a face, take my face. You train an encoder to learn my facial features. Then you train a decoder, decoder A, to be able to reconstruct my face. Then you take face B, we'll take Kerm's face. You train a different encoder, encoder B, to learn Kerm's facial features. Then you pass that through a decoder, which has learned how to take kind of that representation of a face and recreate Kerm's face. Another way to think about it, which I think is more useful going forward, is to think of houses. So the first row here is like, a traditional brick house with regular shingles. So, you take an architect, which is your encoder, and you have the architect learn how to create blueprints of traditional brick houses. You have them visit 1,000 traditional houses. They walk through the house and they learn how to create a blueprint. That's your latent kind of blueprint. Then you give that blueprint to a builder. And that builder then goes out and builds you 1,000 traditional brick houses. And so that builder becomes very good at building traditional brick houses. You've trained it to be very good. Then you take, in the bottom row, kind of a modern flat roof, lots of windows house. you have an architect, walk through 1,000 modern houses. The architect gets very good at creating a blueprint for a modern glass house. Then you give that to a separate builder, and now you have that builder build, 1,000 modern, flat roof, really, nice modern houses with lots of windows. So builder B is very good at building modern houses. Builder A is very good at building traditional brick houses. So now you want to build a house. You meet with an architect, they give you blueprints for a nice traditional brick house. But then you change your mind, like, I really like the inside, but I want my house to look like a modern flat roof, lots of windows house. So then you take your blueprints and you meet with builder B, who's very good at building the modern house. And you say, you know what? I have these blueprints. I want to keep the inside the same, but can you make the outside modern? Put more windows, make the roofs flat. And because builder B is very good at building a modern house, it's very simple for builder B. Yeah, give me the blueprints. I'll keep the inside the same, but I'll change the outside. And that's essentially what a deepfake is. You're taking some sort of, a house or an image or a face, and you're transforming it into something else. And you've trained, both an encoder and a decoder, an architect and a builder to be able to build those things. Now, food for thought, in this example, if you wanted to build a modern house, think of, if you wanted to save money and time, do you actually need an architect? If you meet a really good builder who can build any type of modern house, do you need an architect to make it happen? And then future slide, we'll talk about that. But for now, we'll kind of have that, architect, builder, encoder, decoder. So with that concept, that's how you actually transform, say, an image from one type of image to another type of image. You can transform, a zebra to a horse or vice versa. You can transform a photograph into any other style, a Monet, a Van Gogh, what have you. You can convert a winter scene to a summer scene. And again, it's all just, you feed an image into an encoder, it creates some sort of blueprint, you feed it to a different decoder that's very good at creating a certain type of image. And you can do that with video as well. So a few kind of interesting video clips.
On some of the supporting guys, but he was like trying to place me, So he sat down next to me, he's like,
So Bill Hader turns into Tom Cruise.
I love your work. And I went, oh, thanks. I love your work too, Tom.
And then this is just a person who has...
So just remember, if you're on fire, stop, drop, and roll. One more time. Say it with me now.
Stop, drop, and roll. Do that. Do it.
So obviously that's not Keanu Reeves. That's somebody's face, and he's taken his face and be able to put Keanu Reeves onto his face, just like that fake Obama example. And also you can do the same thing with voice. And so that's how you take one person's voice and you can transform it into another person's voice. Okay, so that's called generative AI, generative learning. So how do we take that back to LLMs? LLMs are actually, based on that encoder decoder network. And so how do you translate a language? So you basically take, in the example of the house, right? You take a traditional house, in this case, English, you feed it through an encoder to capture the representation of that language. Then you take that representation of language, and then you feed it to a different decoder. And in this case, it's German, and then it outputs something in German. So then you basically feed an English sentence through the encoder, it sends that representation to a different decoder, and that decoder converts that into German because that decoder B, is an expert at the German language, giving you German. So that's how Google Translate, all these translation programs work. So it's an encoder decoder network. Okay, so now let's talk about, so how does a chatbot like ChatGPT or Gemini or Claude, how do they work? So, if you look at this row here, say instead of training your architect and your builder on modern houses, you basically take every house that's ever been built on the planet, and you're able to train an architect to be able to create blueprints of every house that's ever been built, modern, traditional, European style, whatever, bungalows. Then the architect can create a blueprint, and then you have a decoder builder that is an expert at building you any type of house that you want. It's that well trained, and so that's kind of what ChatGPT was trained on. It took the totality of English language it could get access to. It trained an encoder to basically learn how to encapsulate the English language into sort of a latent space, a blueprint. Then it trained a decoder, sort of like a builder, to recreate the human language. So that's how it's trained. So it's kind of this encoder decoder network to train an encoder and decoder on basically on the human language, what it is, how to recreate it. And remember I asked you before, like if you want to build a house and you had a builder that was an expert at building any type of house that you needed, do you need an architect, or can you just go to that builder and say, I want a house that's modern, has 3 bedrooms, 2 bathrooms, 3-car garage, 10-foot ceilings? The builder, if they're expert enough, can probably do that without any sort of blueprint. So that's actually what the final version of ChatGPT is. It got rid of the architect, the encoder, and is only just the decoder, the builder. And you feed it your prompt, and the decoder, the builder, is so good at human language that it can answer your question in human language because that's how good of a builder it is. So ChatGPT and all of the kind of flagship LLMs are really just a decoder. They've gotten rid of the encoder for computing and efficiency's sake. Okay, so that was good timing. So that is the basics of how LLMs work. So that's cool. That's interesting. I think it's super interesting. So then what is Epic doing with all of this? And the answer is they're doing a lot. They're I think on the leading edge of incorporating all of this AI technology into Epic. So there's 4 different areas, and the first area I want to talk about is what I call cognitive computing models. So this is analogous to that very first simple example I gave you of trying to predict something like ambulance offload time. This uses very simple kind of statistical or simple machine learning algorithms to predict some sort of outcome or number. So Epic has built in a bunch of these validated algorithms. To deploy it in a hospital, you need to internally validate and test it, then you pilot it, and then you kind of roll it out. So at St. Joe's, something called the deterioration index, which is an index that predicts a number, which is the risk of a person deteriorating. So that was previously deployed many years ago, but there's some issues with Health Canada approval. So then that was paused, and now we're working on redeploying it, retesting and redeploying it. We've worked over the past several months on validating a model that predicts the risk of an inpatient fall. In the past, it was done using something called a Morse score, which is a kind of very manual that the nurses had to do. So this particular model is done automatically in the background. And again, it's trying to predict the risk of a patient falling. We've successfully piloted it, piloted on a few units, and the plan is to deploy it on more units in the near future. And we're starting some initial discussions on whether we can use a model to prioritize CT scans, emerge and inpatient scans. So it assigns a number, the number might be 850, another CT scan might be assigned a number of 700. So the scan that's assigned a score of 850 is potentially higher in urgency than the one that's a lower score. So we're working on kind of the initial discussions of how we can implement that kind of model. So that's kind of very traditional, very straightforward, traditional statistics or machine learning models. So number 2, so this is new. I think other hospitals have started to roll this out in the last couple of years. At St. Joe's, we are maybe going to be doing this soon. Not quite sure. There's some, issues that we can talk about in the question period if people want to ask. But this is what's called the Generative AI Suite. So it's using an LLM like ChatGPT, Gemini, Claude, and using it to do something for you. And so in this bottom left picture, so remember that we talked about having a decoder, that is trained on the human language. Um, and so what if we took that builder, for example, and we said, and that builder can build any type of house imaginable, but you tell it, you know what, I have a picture of 10 types of Spanish, terracotta, Spanish type houses. I have these 10 pictures. I'm going to give you these 10 pictures and build me a house that looks similar to one of these 10 houses. And so you're basically you're constraining your LLM to a certain knowledge base. Not anything you can do, but you're saying, I want you to just focus on this. And so that's a concept called retrieval augmented generation, RAG. So that's where you have an LLM that can do anything, but you feed it some sort of data that constrains what it does. And so for those of you who have used open evidence, if you haven't, you should use it. It's amazing. But for those, so that's how really open evidence works. It takes, one of these flagship LLMs. I don't think they actually tell you which one they use, whether it's OpenAI or Google. And you feed it high quality data. So you feed it all of the, research that's been published from New England, JAMA, Annals of Internal Medicine, Annals of Surgery, like high quality journals. And you constrain, say, ChatGPT to only use that data source to answer your questions, just like the builder. Like you wanted to build a Spanish terracotta house. And so you get much more accurate data with much less hallucinations when you can use RAG, retrieval augmented generation, to constrain your LLM. And that's essentially how all these generative AI features work. So I'll touch on a few of these. So draft hospital course in discharge summary. So we're working on kind of being able to optimize discharge summaries to make it more useful for our family medicine colleagues. But residents and attendings don't have time. So maybe their discharge summaries are very short and don't include a lot of information. But what if then you feed all the notes from this stay into your LLM and you constrain it to that information and you tell your builder or your decoder, this is the data. I want you to summarize this data for me. And it's very good at doing that because it's constrained by the feature set, that the data you give it. So that, that's how things like draft hospital course works, inpatient insights, outpatient insights, end of shift care plan notes for nurses when they're doing their handover, can summarize what happened on the previous shift for the incoming nurse. So these are some pictures I took from Epic's annual conference back in August. So this is kind of Mayo Clinic's experience rolling out some of these features. So this is the outpatient insight. So again, this is feeding, some subset of data to your LLM and have it summarize things for you. So it can summarize notes, provide citations, links to the actual note that it got the information from. It can highlight relevant text. It includes internal and Care Everywhere data. And so if you look at the pictures here, so this first panel, so that the patient summary, they have coronary artery disease, had an MI in 2023, they had an angioplasty, they have hyperlipidemia, it's well managed with the current medications, the LDL cholesterol is within the target range, they have hypertension, they have type 2 diabetes, it's uncontrolled despite metformin, their last fasting glucose was this, their last A1C was that. And then you can kind of dive in to get more details about, what happened during that angioplasty in 2023, 2022, and some of the details about their coronary artery disease. So it basically does what, would take you many, many minutes to do and summarizes it to make your life more efficient. You can do the same thing with inpatient insights. So it can create, admission summaries. It can create you a patient story. It can tell you the recent events that happened since the last time you were at the hospital or on service, some kind of recent events. And again, so this is kind of the notes summary. So for respiratory, it says the patient's respiratory status has improved, less distress, better airflow. They're weaning from the vent. It gives you some nutrition information. Patients on TPN tolerating well, slight improvement in albumin levels. There's a wound on the right arm. So instead of having to go through lots and lots of notes, it gives you a nice summary. And again, this is kind of a patient story summary that gives you more details of the patient story. So again, what would take you, many, many, many minutes to do, you can be more efficient with just reading a generated summary. And then the final thing I wanted to touch on is the hospital course generative AI feature. So this is creating a hospital course to put in your discharge summary. So then, it kind of generates this: a 14-year-old male was admitted to the ICU, had a splenectomy, open reduction, internal fixation. So it kind of gives you the course in hospital. So I hope you're thinking, this looks great. This looks like it saved me so much time. But how accurate is it? So there's starting to be studies published. So this is a study published in JAMA in August of last year, so a few months ago. And this was a study that used Epic's hospital course and discharge summary AI feature. So it's summarizing a hospital course. And they tested to see how good it actually was. So what they did is they took 100 hospital admissions that had a discharge summary created by a physician. Then they fed that information into an LLM to have the LLM generate a hospital course summary. So you have a physician generated one and an LLM generated one. Then they took 10 residents, 8 attending physicians, and they gave, maybe 10, to 12 charts to each person. And they allowed those people, the physicians, to review the charts for 10 minutes so that they could get a sense of what happened to that hospital during this day. Then for the residents, so the resident has 10 charts, they gave that resident the physician version of the hospital course and the LLM version of the hospital course. And they gave the residents 3 minutes to edit those discharge summaries. And then they graded and they looked at how many edits were required by the residents to get it up to a standard that the residents thought were a good discharge summary. Then they took those resident edited hospital courses, both the physician edited, the one that they edited written by a physician and the edited made by an LLM, and they gave both of those to the attending physicians. And remember, the attending physicians have read through the chart for 10 minutes. They know what happened, and they're given these two resident edited hospital courses. And then they had to grade which one they thought was better. And they were blinded, so they had to grade whether they thought, one was better than the other. And so these were the results. So they found that the resident edited a smaller percentage of the LLM written hospital courses than the physician one. So the residents didn't have to make as many changes to the LLM generated hospital course. And the attending physicians thought that the LLM hospital course summaries were more complete, similarly concise, and similarly cohesive. But there were more confabulations, so more hallucinations. So two takeaways from this. The LLM generated hospital course summaries were more complete, so they provided more information to the family physicians, and they were just as concise and cohesive, but there was a chance that it made things up. So, this reinforces the concept that, AI as it is now still needs a human in the loop. You can't just set it and forget it. You still need to have a physician review the output of AI. But so I think we're going to see more papers like this that show that generative AI is going to make physicians' lives better. So that's kind of the some of the studies that are done for the generative AI suite. Okay, so in the last few minutes, I want to talk about what I think is very exciting. So it's something called Cosmos and Curiosity. So Cosmos, so Epic has been very smart. I think, people say that data is the new oil or data is the new gold. Whoever has the most data has the most accurate algorithm, has the most power. So Epic has been very smart. So any hospital that uses Epic, if they agree to contribute their patient data to this huge repository called Cosmos, then they can access Cosmos. So lots of hospitals, so over 1,800 hospitals, submit their patient, all of their data from Epic into Cosmos, which is controlled by Epic. It's de-identified, but it's a huge data set. It has 300 million longitudinal patient data. over 18 billion encounters, almost 9 billion face-to-face visits, several thousand clinics, 1,800 or more hospitals, and data from, almost 500,000 physicians. So they have 300 million and growing longitudinal patient data, all fed into a data repository. So that's a lot of data. So what can you do with that? So this is another slide. So for providers, there's something called lookalikes. And again, we don't have Cosmos at St. Joe's or HHS, though, we haven't been able to play with it. But, this is what's advertised. So for providers, something called lookalike. So if you have a patient that, it's just a diagnostic dilemma, their blood work shows this, their imaging shows that, but you just can't put it all together, you can feed that patient information into Cosmos, and Cosmos will search through that 300 million patients that it has and try to find a lookalike patient, a patient that is similar to your patient that you're not quite sure what's going on. Now, Cosmos will not provide you with that patient information, but it will provide you with the name of the physician who's looking after that patient. And then you can contact that physician and discuss, is your patient similar to their patient? So that's very helpful. It can do something called best care choices. So, you might have a patient with diabetes, A1C is 8.3, and the patient's not on a certain medication. Cosmos will say, well, for similar patients like yours, other providers have their patients on, this other medication. 80% of other providers with this type of patient have their patient on Ozempic or whatever. Antibiograms are pretty interesting. So, there is a little bit of geographic information in that data set. So, if you have a patient with H. pylori, to use a GI example, it will say, well, in the Hamilton region, you have a high incidence of, say, clarithromycin resistance or metronidazole resistance. So maybe you want to use a different antibiotic because of the resistance patterns that EPIC, it's in the EMR, you can access all that data. For operations, you can talk about things like length of stay. So, for certain patient kind of presentation, it can estimate length of stay based on other similar patients in its database. And then for patients, if there's a rare disease, in that 300 million patient data set, there may be another patient that's very similar to that patient. And so maybe there's a more accurate growth chart to be used. Okay, so that's Cosmos. And for research, I think if ICES in Ontario has lots of data, but I don't think they have 300 million patient worth of data. So Cosmos is kind of like ICES supercharged on steroids, but with less bureaucracy, because you can go into Cosmos with appropriate permissions, but you don't have to go through all the red tape of getting access to something like government or ICES data. And you can answer questions just like you can with administrative database research. So that's Cosmos. We'll end off with Curiosity. So this is what I think is super cool. So we've talked about how you can generate, you can have a decoder build you a house. You can have ChatGPT, a decoder builder, create human language for you because it's been trained on, all the houses that have ever been built. It's been trained on the totality of human language. But now you have a Cosmos data set that's trained on 300 million longitudinal patient data. So, it has a lifespan of a patient from when they're 30 to when they're 90, potentially. And you have 300 million of these patients. So then so you're almost training a encoder decoder network on human health history. So then you do the same thing as you do with ChatGPT. You train your encoder decoder network. You keep your decoder, which is very good at being able to tell you the course of a patient's history. Then you feed in at the top here a patient's history. And because your decoder is trained on all this data to be able to know what a patient's outcome is going to be, you feed your patient, 78-year-old with a history of heart disease, diabetes, A1C is 7.8, LDL is 4.5, had a heart attack 5 years ago. Then you feed that information into your decoder, and it tells you, well, this patient, based on all the other patients it's learned from, has a 20% chance of having an MI in the next, 2 years. And so that's basically the concept of Curiosity. It's basically, so they, instead of calling it a large language model, they're calling it a large medical model. So you feed in a patient's whole health history, office visit, abdominal pain, diabetes, A1C, and then you run it through the decoder, and it simulates like 100 potential future scenarios. And it says that of those 100 scenarios, 16% of the time they had a COPD exacerbation in 1 year. 25% of the time they had a hospitalization at 3 years. And so that's kind of, you're taking what ChatGPT does, but you're doing it with past medical history and future medical events. Oops. And so, have they published a paper? Yes. So this is the paper published. This is kind of new, cutting edge, just published. Researchers at Yale used this concept, and they trained a large medical model. So this is interesting because I think if you look at this abstract, it covers all of the information that we talked about. So, it uses the Epic Cosmos data set with medical events. They call it curiosity models. And this is interesting. So it's a family of decoder-only transformer models. So we talked about this, right? ChatGPT only uses the decoder, and they uses that transformer architecture. It has 118 million patients representing 115 billion discrete medical events. And they put bracket 151 billion tokens. And tokens are actually kind of like the weights. Remember that image? We had lots of different weights on all the different arrows. So this model has like 151 billion kind of these weights. And Curiosity predicts the next medical event to simulate patient health timelines. So they studied it on 78 real-world tasks, including trying to predict diagnosis, disease prognosis, healthcare operations. And they say, remarkably, for a foundation model with generic pre-training, Curiosity generally outperformed or matched task-specific supervised models on these tasks. So again, this is early days. This is like the first paper published on this. But it looks like it has promise to be able to predict future events. And again, we talked about data versus performance. So as data goes up, performance gets better. So as more and more hospitals contribute information to Cosmos, Cosmos should only get better and better and have better performance and be more accurate. And so this is my final slide. So I took this from Epic's website. So it says, Curiosity will be able to simulate a patient's likely future trajectory and summarize key insights such as extended hospitalization, 30-day readmission, cardiac risk, emergence of conditions like pancreatic cancer. And they talk about the results of the study. And then it says, starting in February 2026, so this month, research from Cosmos participating organizations will be able to explore Curiosity in a virtual lab to play with it, look at new use cases, and advance its clinical relevance. So this is kind of hot off the press. They're just releasing it now. Hospitals have to submit to Cosmos before they can do any of this. And there's, there's issues with trying to get onto Cosmos from a privacy perspective, which we can talk about in the questions if people are interested. But this, I think, Cosmos and Curiosity this is the future. So, if there's any trainees on the call or kind of people who are interested in research, I think this is the future. Previously people did a lot of ClinEpi type research, but I think large data health research is now going to take off. This is the start, I think, of large data health research. And you can do it because of things like Cosmos with huge repositories of patient data. Okay, so concluding remarks. So, I think we talked about a lot of technical things. Hopefully it wasn't too boring or too detailed. I sort of liken it to the kind of learning basic science. So once you know basic science, then you can apply the basics to real world use cases. I hope people are excited about what Epic is doing with AI. I think it is super interesting and leading edge. And then my take home is that as frontline physicians and healthcare workers, I think we need to seize the opportunity to embrace AI. There's funding issues. I think we need to advocate for hospitals and clinics to invest in some of these AI features so that both us as a profession, burnout, efficiency, and our patients can really benefit from these technologies and nobody gets left behind. So that is it. Thank you very much.
Thanks, Charlie, that was great overview. Lots to reflect on. I'm probably going to watch the video a few times to try to understand it all. There's a few questions. I know people have raised their hands. I think Dr. Holbrook, you're first. You can go ahead if you like. You can also use the chat for those who are able to use it for questions.
And I think you're muted.
Oh, there we go. Yep. Thanks very much. I was just chatting. Thanks, Charlie. That's probably one of the most accessible talks on AI that I've heard. That was really lovely and clear. I just wanted to offer a perspective and ask you a question. So I might be one of the few people in Hamilton that has worked with ICS data and with EMR data in research for decades. So as you say, things are developing, but I would say there's some major cautions as well. One of the beauties of ICS data is that you get a well-curated, well-cleaned data set, and you get expert analysts who know what they're doing in terms of statistics. Of course, the downside is it's limited amounts of data, and there's things that we have in hospital that ICS definitely does not have, but there are benefits. I mean, the hospitalization is kind of in a lot of ways, a black box in terms of ICS. So for example, in my field of clinical pharmacology, Epic tells me what was actually administered to the patient, not just, what was dispensed at the pharmacy. But Epic's been a struggle. So I just want to let people know that all EMR data, of course, needs validation for data quality, because use in clinical practice is a much lower level of quality than use for research. So one of my grad students has spent 2 years of his life as one of our pharmacists, Tyler Schneider, validating Epic. So it's great in a lot of respects, but is lousy for diagnoses. So Epic data, if you're pulling Epic, Dovetail it'll be the same in Odyssey at HHS, is very poor on diagnosis because we're not forced to enter that information. And Chi-Hi, which we're linking to, only has a few mandated fields. So there's definitely work that needs to be done there in natural language processing. And you probably know we had a group that was going to have Hamilton joining Cosmos, was running smoothly for a long time, then came to a very abrupt halt over what I understand is privacy concerns, that the data is actually held in the US at Epic Systems. And we're Canada. I have also some concerns about the use of US data, but that's kind of another story. But I wondered, that's my question. Do you have any further clarity as to where we're at so that Canadian hospitals can join Cosmos?
Yeah, so great question. So the first part of your comment is, I agree. I think they're complementary. So I think ICES, Gemini, that Unity Health, the database they have, and Cosmos, I think they're all complementary. I don't think one will replace any of the other ones. To answer your question, so it's related to what's considered PHI. So the data is de-identified, but the postal code is there. So we've been told that having the full 6-digit postal code, you can reverse engineer that to actually identify potentially an individual patient. So then we said, well, can you use the first 3 digits, the forward sortation area, the first 3 digits of the postal code? And there's debate among experts about whether or not just the first 3 digits is enough to consider that de-identified so that it is no longer considered personal health information, PHI. Because anything with PHI cannot leave Ontario or Canada according to Ontario laws. If it's not PHI, then it can go to the states. So the question that's debated is the first 3 digits of a postal code attached to de-identified patient information, is that sufficiently de-identified to say that it is no longer PHI? And there's debate. So I think a lot of hospitals are trying to work through that. Other hospitals have said, well, we're in a new era. There's a risk in everything we do. We sort of have to balance the benefit versus the risk. And some hospitals, like Ottawa Hospital and the Central East region, that big conglomeration of hospitals, they've actually gone live with Cosmos. They know, some of these issues, but their opinion is that, the first 3 digits should be enough to de-identify it, and it's not considered PHI, and they have gone ahead with Cosmos. Other hospitals are being a bit more conservative, including St. Joe's, HHS, and many other hospitals. And all these hospitals are kind of approaching it together to try to figure out what the next path is.
Yeah, interesting, because ICS uses the forward sorting area, the first 3 digits as well. Thank you. Thanks again.
I think that data stays in Ontario. I think that's a difference. Because if the first 3 digits is considered PHI, then it can't leave. Yeah.
Dr. Levine, your hands up. Go ahead.
Okay, I'm unmuted now. Okay. Thank you for an excellent talk. You talked about the hallucination problems, kind of the stuff that's coming out of the other end that's false, and I appreciate the need for kind of a human filter on that. But my bigger concern is the data that goes into this whole process comes from humans a lot, with lots of error. And so we are actually the part of the problem. And how does it address? Like when you look at a patient's chart, I have no problem. The lab sends the data, lab results, probably 99.9% correct. But people put things in their notes that are factually wrong and never correct them. I mean, we see it all the time when we get certain drugs forward. This patient's on this drug and it keeps getting forwarded and forwarded and forwarded in notes, or something happened last year and it continues on as part of their past history and it's wrong. So how do we address this false information getting into the system that gets perpetuated by the AI models?
Yeah, that's a great question. It's like the whole garbage in, garbage out kind of saying that if what you're feeding into the model is not good quality, then you're not going to get good quality out. So part of that is the data cleaning aspect, is like, trying to feed in good quality data into your model to try to get something better out. Part of that retrieval augmented generation, RAG, is to try to address that a little bit. That's why I think open evidence is so good, is that, ChatGPT has been trained on, potentially some quote unquote garbage text. So then you try to restrict your model, your decoder, to a subset of data that's better. And then your decoder can read through and sort of restrict itself to higher quality inputs. So I think retrieval augmented generation is one of the answers to that. It's not the only answer, but short of teaching everybody to write better notes, and yeah. So I think RAG helps to solve that a lot.
Hey, thank you.
Thanks so much. We're just approaching 1 o'clock. There's some comments in the chat. I don't know if you had a chance to look to Charlie, just about how these models can be trained, and I think it's similar to the comment that you just made about the utility of them based on inputs. So if you have any comments to those comments.
So is there any research on the use of AI in this manner? Example, discharge, subject pooling data I actually don't know, because I'm kind of new to Hamilton and sort of the academic setting, because I was in Brantford before, but I don't know how much of this is being taught to medical learners and trainees. And so, how does this impact learning and trainees? I don't know the answer to that. I think that's an interest of mine, is like, how do we teach trainees to incorporate these things, to use it wisely, and catch things like confabulations and hallucinations, and not just blindly follow it. So I think there's a lot of education of what it can do, what it can't do, and being careful with it. Because with healthcare, obviously we have to be very careful. You can't just trust it. So I think the medical learners aspect, I think, is important, and something we need to start dealing with, because in my master's program, everybody is using ChatGPT, and it's crazy. They're not writing their own papers anymore, and courses are not adapting, so that you have to come into in person and you create pictures as your assignments. So it's no longer just writing a paper for your final assignment. It's coming in and drawing things and writing things on a piece of paper. So we've kind of almost gone old school. And so how do we adapt medical education for this new environment, this new era? I think that's very interesting.
Excellent. So it is 1 o'clock. To be respectful of everyone's time, I'd like to close the session by thanking Dr. Charlie Wang again for outstanding, provocative, and relatively, I think, easy to understand and follow presentation, although it will be posted for anyone that wants to review it. I know I will. And thanks again. Have a great rest of your day, everyone.
Thanks, everyone. Bye.